Venice, a city famous for its art, cultural heritage, architecture, and of course, the canals. But recently, these canals have been flooding frequently due to a dramatic phenomena called aqua alta. Scenarios where a high tide which causes partial flooding is known as aqua alta. Venetians may have adjusted to aqua alta, but it seems the buildings of Venice are not ready for it. With the constant saline intrusion into the city, salt weathering is slowly damaging the buildings and its infrastructure, hence leading to frequent maintenance work. Such situations of flooding and salt weathering are increasing with times and will only get more frequent in the following years. This brings our attention to think that are the current building methods and materials fit to resist salt weathering? Therefore, we introduce you Biochroma, a revolutionary bio-integrated design which proposes a new construction strategy for marine environments. It uses traditional construction materials coated with novel substrate material that can potentially withstand salt weathering, allow biocoloration, potentially clean air on algal growth. Algae are photosynthetic organisms that sequester carbon and can induce natural coloration on growth. The aim was to immobilize algae over building facades as a strategy, to clean air and use the contact of seawater as a strategy. Through extensive research, a novel hydrogel-based substrate material was developed for architectural application and appeared promising with less shrinkage and better strength compared to a regular alginate-based hydrogel. This was done by introducing plant-based fibers with a chemical composition of cellulose, hemicellulose, and lignin that allowed uniform fluid transport of the cross-linking agent, ensuring a stable 3D matrix of hydrogel composite. The compressive strength of a dehydrated hydrogel composite could nearly match similar to as a regular sun-dried brick. The hydrogel composite substrate is used as a mortar to bind bricks together. The cross-linking of hydrogel with plant fiber provides high mechanical strength. And yes, you can pick it up as well. The substrate is also used as a surface coating. Being a hydrogel composite, it has high water absorption capacity, and current tests show that the substrate is immune to deterioration of saline water for more than a period of 3 months. Due to water absorption, it naturally favors algal growth as a substrate and proven receptive to series of marine algae.
To optimize the functionality of the material application and rethink over the design of a traditional brick, we parallelly remodeled the design of the brick so that it can achieve stability on interlocking. The modules were designed to be tessellations and optimized to promote strength, porosity, to maximize the point of contact but minimize the surface area for material application, and surface flow for algal growth. Through a series of design iterations, we informed the fabrication methods for casting real scale bricks. The bricks were designed to be hollow and solid and fabricated using simple casting methods. Molds were critically designed for solid casting and slip casting. The hollow and solid bricks were casted and fired for prototyping and application of the substrate material.
A series of prototypes were plastered with the substrate material and glued together with the same material on cross-linking. Further, a red marine algae, Porphyrium purpureum, was upcycled with seawater for algal growth. The algae produces red biofilms that adheres to the substrate, while the substrate stays hydrated being in hydrogel composite. The phycocerathine in the algae produces red pigmentation that on dehydration induces appealing hues of pink, ensuring biocoloration. The dripping seawater and the pink coloration over the substrate creates an ideal scenario to add on to the architecture for the marine. And the play of expansion and contraction of the hydrogel substrate speaks more vibrance than the color itself.
Exploring the tessellation and upscaling of the modules allows us to envision the growth of algal species such as Peripodium and Cyanococcus. A series of radiation analysis was done with various design modules to explore self-shading. CFD analysis further allowed to speculate the Venturi effect through air pockets between the bricks, which can potentially allow passive cooling. Developing hollow bricks also allowed internal water flow, creating vertical channels, and can be used as a strategy for water storage and irrigation of the substrate. A thermal study confirmed solid bricks showed more thermal lag than hollow bricks. We developed an algorithm which follows discrete design logic to generate cellular forms and functional architectural spaces. Discrete design is informed by a source and a target. The growth is controlled to inform porosity, density, and direction. An open space biocanal was selected in Venice. The source points for the discrete were generated based on the circulation over the site. Radiation analysis was used to generate a volume on the site that informs the target surfaces for the discrete. Multiple simulations are conducted from each source point to generate a volume that is translated into an architectural space. The verticality of the structure justifies the load-bearing nature of the bricks carrying seawater for growth that colorizes naturally, potentially cleans air, and can endure scenarios like aqua alta. Further, sun radiation analysis informs manual seeding of different strains of algae based on thermal zones for biocoloration and beautifying the experience of the space.
Adding to the words Venustas, Utilitas, and Formitas by Vitruvius, Biochroma proposes Viota, living for the future.